Hello and welcome to this lecture. We will consider three different things in this lecture. We'll begin with this notion of repeated independent trials, which results in something called Bernoulli trials, which are very important. They are often used in practice when you want to collect some statistics and make some inferences, etc. It's very important. And two distributions which are closely associated with Bernoulli trials. One is independent Bernoulli trials. One is called the binomial distribution, the other is called the geometric distribution. So let's get into these three things. So we'll begin with Bernoulli trials, and let me just begin with some sort of an application or a setting where something like this arises very naturally. Okay, so quite often the government or an administration of a city is interested in finding out incidence of a disease, as in there could be some disease, a flu or any other disease among the population, and they may have a sense of it, and they may want to collect some statistics about it, as in they may want to know what fraction of the population maybe that's infected. So this can drive policy, right? So they can do something for such people, devise some strategies for that disease, figure out if it's if it's an epidemic or if it's endemic, and then do something various. There's lots of things you can do once you know things like this. So one thing they may do, like for instance, to generally assess how bad is the spread of the disease, is to pick a random person from the population. Notice what I'm saying is random, so maybe they're just walking around and just find someone there and catch them, and then administer a test for that disease, right? And they may repeat this in different places at random times in various locations. Hopefully that person is actually in the city and not just passing through, right? So they can do these experiments, and so these kind of things one can call as a trial, right? So it's a trial. So maybe they repeat it n times, and maybe one can assume that each of these trials, in the sense that the person you picked from the population is maybe some random enough that you assume it's all independent, right? So hopefully they're from different places, and they don't have maybe a connection and things like that. So you assume these are independent, and the number that you will get at the end is how many of these tested positive, right? So there is a test, and and that test, let's say, is a very good test, and if somebody has the disease, it will turn out positive. Otherwise it will turn out negative, and then in that case, finally at the end of n trials, you have this number with you. Okay, so a natural question that arises is, what is the distribution of this number, right? You need to know what's going to be the distribution of this number as a function of the actual incidence of the disease, right? So if you expect this number to be high, if a lot of people are infected in the city, if you expect this number to be low if a few people only are infected, and you want to get a sense of the distribution of this, right? So you want to know what the PMF is, what the what the probability that this number is a certain value, right? So all these things you want to know. So more interestingly, maybe you want to infer from this number what fraction of the total population actually has the disease, and this might help you, with budgets for how much you have to buy, and etc. etc. Okay, so this is just a setting, and sort of brings out this notion of a trial and its importance in practice. So how do you mirror this in theory, right? And then the theory that we are studying, how do you understand, or how do you have a framework for something like this? Okay, so let's ask that question, and from there you get this notion of a single Bernoulli trial. Okay, so here's the setting. You have an experiment, and then there's a sample space associated with a set of all outcomes, and there's an event A inside this sample space, some event, and we want to consider this occurrence of this event as a success for us, right? You go back to the disease. What is this event? This event is the fact that the test was positive, right? So quite often when you do trials, there's going to be an event which is a success, or when I say success, I mean it's not in the positive term, it's just that it's something that you want to count, right? It's a 1, not as opposed to a 0, which corresponds to a failure you're not interested in. If somebody did not test positive, that's like a 0. Somebody tested positive, it's a 1, and you add all of those ones together, you get the total number that tested positive, isn't it? So something like that. So this is what the setting is, and let's say the small p is the probability of this event A. Okay, so once again, there's an experiment, and there's a sample space, and there may be so many events associated with that sample space. I'm not interested in all of them. There's only one particular event A which I'm going to think of as being critical for me in my trial. I'm interested only in that, and if that occurred, right, when you did the experiment, if that event A occurred, I'm going to say I have a success, I have a 1 as opposed to a 0 when I have when I don't have event A occurring. So for the Bernoulli trial, even though so your random experiment may have lots of other outcomes, but I'm not interested in all that. I'm only interested in success or failure, right? I'm only interested in whether event A occurred or A complement occurred, and one of these will definitely occur all the time, right? So either A occurs or A doesn't occur. So I'm interested in this Bernoulli trial only in a sample space with 2 entries. My outcomes are just 2, either success or failure. Okay, whatever it is my experiment may be, my experiment may involve a complicated blood collection, and then numerous tests and numerous results may come, and then finally they may say, yes, this person has the disease, this person does not have the disease, right? My interest in a Bernoulli trial is in only that success and failure. I'm not interested in anything else that you might have done in the actual test, okay? And my probability of success, my probability that the event of interest occurred is P, okay? So instead of saying success, failure and all these things, one can simplify this and make the sample space into just 0 or 1. And probability of 1 is P, probability of 0 in this very simple sample space is 1 minus P, okay? So this particular distribution, okay, sample space of 0, 1 with the probability of P associated with 1 and probability of 1 minus P associated with 0 is called this Bernoulli P distribution, okay? So you can see quite easily how this becomes a very nice framework for things like incidence of a disease and testing from, picking a random person and testing. All right. So this is a single Bernoulli trial, and as you can see, as you can expect, we're going to repeat this multiple times independently and see what happens. Let's look at that. So we're now going to consider repeated Bernoulli trials, okay? And the setting is sort of similar to the previous setting, I mean, you have an experiment which you do, and there's an outcome of interest, and you just have success and failure in mind in your sample space. You do it once, you have success with probability P, that much okay? Now you can repeat this multiple times. Supposing you repeat this n times. So anytime you have these independent trials, there'll be these 2 parameters. One is the probability of success P, and next thing is the number of times you repeat it independently. That's n, okay? So n times you repeat the single Bernoulli trial, Bernoulli P trial independently. So that's the setting, right? So you keep repeating it, and now your outcomes are many more, right? So if you did it only once, your outcome is either 0 or 1. Now you have n trials, and in each trial you could be 0 or 1, okay? So there are 2 possibilities for each trial, there are n of them. So 2 into 2 into 2 into 2 into 2, n times, that's 2 power n outcomes. So your outcomes are much larger in number, and let's look at some simple examples first. So supposing you look at n equals 3, if you did it only 3 times, your sample space will have outcomes which are 0, 0, 0, which means 3 failures, 0, 0, 1, 2 failures and a success, 0, 1, 0, failure, success, failure, so on till 1, 1, 1, which is success, 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 okay? You could have n equals 4, in which case your sample space will keep growing like this, 0, 0, 0, 0 to 1, 1, 1, 1. Okay, so those are the possibilities that are listed here. To compute probability of a particular outcome, you can use independence and write down the expression quite easily. Okay, so I've shown you some examples here to illustrate how it is done in general, and you can quite easily extrapolate this. So let's look at n equals 3. If you want to find the probability of 0, 0, 0, okay, that's the probability that I got a 0 in trial 1 and 0 in trial 2 and 0 in trial 3, and importantly these 3 trials are independent. So you can just multiply the probability of each of these things. So you get 1 minus p times 1 minus p times 1 minus p, that's 1 minus p power 3. So given a value for p, you can find the probability of 0, 0, 0. Not just 0, 0, 0, any other outcome, 1, 0, 1 I've shown you here. It just works out as p squared times 1 minus p. You can take anything else. So let's say I take, this is on a pen, and maybe I should pick a blue here. Let's say I want to take probability of 1, 1, 0, 1, right? So that's going to be p power p times 1 minus p times p, right? 1, 1, 0, 1, 1 in the first trial, 1 in the second trial, 0 in the third trial, and 1 in the fourth trial. So that's just p power 3 times 1 minus p. So like that, given any value for n and given any value for p, I can find the probability of every single outcome in my sample space, isn't it? Just by using the rules of probability, the rules for combining events, one can do this. Okay. So here's a very elaborate experiment with just putting out everything in good detail for you. Supposing you toss a fair coin 5 times. Okay. Now this fair coin actually makes things very, very easy for you, because fair coin, you have to say what success is, what failure is, right? Let's say for my fair coin, I'm going to say heads is failure and tails is success, right? So T is 1 and heads is 0. Let's say I say that. I mean, you can also reverse it. You can say H is 1 and T is 0. That's up to you. I think it doesn't matter much. Okay. And the coin is fair. So my sample space will end up having 32 equally likely outcomes, right? Fair coin is very, very important. You can go back and look at the examples here. If you have H, that is 1 by 32, right? So half into half into half. These are all independent trials. So you get 1 by 32. Any other combination also, you will get 1 by 32 each, right? So it's half into half into half 5 times. So 1 by 32, sample space has 32 equally likely outcomes. You can go ahead and start now computing various interesting probabilities, right? So notice, instead of just looking at every outcome, I can have interesting questions like, what's the probability that when I toss the fair coin 5 times, right? When I do 5 independent Bernoulli half trials, I will get 0 tails, no tail at all, right? That would be H, that's 1 by 32. And I might be interested in 1 tail, okay? So remember, I'm interested in the number of successes, right? That's something of interest to me. So maybe I'm interested in probability that I have 1 tail, right? So if I have 1 tail, then there are just 5 outcomes that are favorable to me, isn't it? Right? 1 tail could be tail occurring in the first toss, or tail occurring in the second toss. Everything else has to be heads, right? Exactly 1 tail is what I'm asking. So H, T, H. So out of 5 tosses, exactly 1 needs to be tail, and that can happen in 5 different ways. So you have 5 by 32 as the probability of 1 tail. So notice these events involve all the 5 tosses, and I can come up with very interesting questions like 1 tail, 0 tails, 2 tails, 3 tails, etc. And I've listed out all the possibilities here. So you notice for probability of 2 tails, you have 10 by 32. There are 10 outcomes that are favorable among the 32. 3 tails is 10 by 32. 4 tails is 5 by 32 again, and 5 tails is 1 by 32. So these are the various different outcomes that can happen to the number of tails that you have in your, when you toss a coin, fair coin 5 times. Okay, so it's just an elaborate little example. Now notice if my coin becomes, so particularly for the uniform distribution, you notice you have this very simple way of calculating how many tails will happen. So it's just 5C0, 5C1, 5C2, etc., right? Because out of 5, exactly 2 needs to be tails. So that's 5C2 possibilities, and I have a uniform distribution, so I can very easily do this. And notice how 0 tails corresponds to 5 heads and all that. Okay, so all this you can do very easily, and then you can have a lot of interesting events, right? I may want probability of at least 4 tails. What is at least 4 tails? 4 tails or 5 tails, right? So that's probability of 4 tails plus probability of 5 tails. And what's the rule I'm using here? I'm using this OR rule, which is the disjoint events rule. So you add the probabilities here, and you get 6 by 32. You may also ask for questions like probability of at most 3 heads. Okay, so what is at most 3 heads? 0 or 1 or 2 or 3 heads. And you add up the probability of each of them, you get 26 by 32. So you notice here, when you have particularly a fair coin, and you're asking all these interesting questions about the distribution, it's just like calculating probability in a uniform distribution, favorable outcomes by total number of outcomes. And then you use your familiar and or rule, the intersection, and for using independence, and or, which is disjoint events, you add them up and you get your answer. Okay, so that's all about the calculations with uniform distribution when you toss a fair coin 5 times. Okay, now in general, the value of P may be different. If the value of P is different and you perform n independent trials, you can do a similar calculation, but quickly the calculation will become a little bit different. So let me just show you a few examples here. Here's an example of n independent Bernoulli P trials, and say n equals 10, and you're given a particular sequence 0, 1, 1, 0, 0, 0, 1, 0, 1, 1. Then you just multiply 1 minus P, 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 1 minus P, 1 minus P, like that, right? So I hope I got that right. Yeah, 1 minus P, and then P, 1 minus P, 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 and so is P power 5 and 1 minus P power 5. Put in the value of P, you get your answer, right? So even though the number of trials may be large, even though the value of P might be different from half or something. Finding probability of a particular outcome, as long as you list it out, is easy to do. It's not very hard, right? So you put it in, you get the answer. So in general, I've given an expression here. If you have B1 to Bn as that string, 0, 1s, etc., all you need to do is to find this W, which is the number of ones in B1 to Bn. I don't care about anything else, only the number of ones. The actual sequence do not matter in the probability, right? Because they're all independent, I'm going to multiply them out together. Okay, in whichever sequence I multiply them in, I'll get the same answer at the end. So probability of a particular sequence depends only on the number of ones in the sequence, and that's p power w to 1 minus p power n minus w. Okay, so I've given you a more elaborate example. If you have 200 repetitions, it doesn't matter as long as you know how many ones are there. If you have 36 ones, right, then it's p power 36, 1 minus p power 200 minus 36. So it's computing the probability of a particular outcome when you repeat the Bernoulli trials is easy even in the general case. Okay, here's a more elaborate example of the same thing, but I want to drive home this point that it's not very hard. You just have to write it down carefully, make sure you account for all the cases, and you'll get the right answer. Okay, so here's a case where I'm tossing a biased coin 5 times. Previously we looked at a fair coin, so everything was half, everything was uniform. It seemed like easy to compute. What if it's biased? What if it's not half, right? What do? Probability of heads is 1 by 3, probability of tails is 2 by 3. Okay, now even then my calculation is not very hard. Why is that? If you look at probability of h, that is simply 1 by 3 power 5. T is 2 by 3 power 5. What about probability of one tail? I have 5 different outcomes, and every outcome has a probability of 2 by 3 times 1 by 3 power 4. Why is that? So supposing you do probability of T, H, that is simply 2 by 3 times 1 by 3 times 1 by 3 times 1 by 3 times 1 by 3, isn't it? It's really simple. So you have 2 by 3 times 1 by 3 power 4. And this guy is also going to give you the same number, this guy is also going to give you the same number, this guy is also going to give you the same number, this guy is also going to give you the same number. And all of these 5 guys are disjoint. Okay, so notice, if you have tails and 4 heads, it's definitely not the same as having this guy. So you can add the probabilities of these things and you will get 5 times 2 by 3 times 1 by 3 power 4. Notice how the answer is slightly different from the uniform case. In the uniform case, you simply got 5 by 32. It was very easy to just simply add the outcomes. Here, you have to add the probability of each of the outcomes. And luckily, as long as you have one tail, this event one tail, probability you have a single tail in this sequence is always the same, 2 by 3 times 1 by 3 power 4. So you don't have to really change the probability for each of these outcomes. It is just 2 by 3 times 1 by 3 power 4. You add up 5 of them, so you get 5 times 2 by 3 times 1 by 3 power 4. Okay, so hopefully this calculation is clear how I got probability of one tail in the biased case to be something like this. Now what about 2 tails? Okay, so if you look at 2 tails, you will see that the probability of each of these guys, right? Probability of each of these guys is actually 2 by 3 squared times 1 by 3 power 3. Okay, so this is wrong, this is wrong, this has got to be 10, this has got to be 10. Okay, so the probability of each of these guys is 2 by 3 squared times 1 by 3 power 3. Why? Because it has got 2 tails and 3 heads. Okay, and each of these things are disjoint in the sense that if the first sequence happened, the second sequence did not happen, right? So each of these things are disjoint, so you can add up all the probabilities. You will get 10 times 2 by 3 squared times 1 by 3 power 3. Okay, notice there are 10 of these cases which have 2 tails out of the 5 tosses that you have. So notice what has changed between the fair coin and the biased coin, right? This 5 and 10 and all remain the same, except that probability of the individual outcome with a fixed number of tails changes. Previously it was all 1 by 32, it was very easy. Here they change, but they change to something else depending on p. Okay, so it's easy enough, except that you have to pay attention to how it's changing. So you can repeat the calculation in the same way. So if you can generalize this, okay, so we will sort of generalize this soon enough. We will look at the general case of Bernoulli P repeated n times, and then we'll ask this question of how many successes you have and all that. So we'll do that. So this kind of calculation is central to the whole thing, and you can see how this calculation is coming about. It just uses independence and disjoint event situation, right? So you just add it up you get the probability. Okay. So I want to go back to the example I started this little lecture with. I started with this incidence of a disease. So let's refine that a little bit. Okay. So let's say a fraction of the people in a city have a disease, and I'm doing this trial where I select a person at random and test for a disease. Okay. So maybe we could make this assumption. We can assume that the probability that a person tests positive is P. Okay. Can you assume P is same as the fraction of the people? When do you think it's a good assumption? Think about it. It's not too bad if you pick the people at random. You don't cluster yourself up anywhere. You pick them up at random in different places. Then it's probably a pretty good assumption. Okay. Now we repeat the trial n times, and you assume each trial is independent. You have a repeated independent Bernoulli P trial, isn't it? So now we are closer to modeling the incidence of a disease in this framework. Okay. And the outcome is number of times the test was positive. Okay. And we are interested in how to think of the number of times the test was positive in terms of n and p. Just like in the previous example we saw, we were interested in the number of tails for whatever reason. And so you see naturally this question of number of successes in n independent Bernoulli P trials arises, right? And that is what's called the binomial distribution. We will go to that next.